So, almost done with chapter 13. We're going to talk next about the polarity of molecules. Polarity of molecules is how the dipoles add up in three-dimensional space. So what are the dipoles? Dipoles are, the polar bonds. The polar bonds are going to have a positive end and a negative end. So this is what this is all talking about. Well, the easiest way to see it is just by examples. Let's just take a look at some examples. So these are some rules, simple rules here. Let's just take a look at something like methane. Methane, the carbon-hydrogen bond, the carbon has electronegativity 2.6. Hydrogen's electronegativity up the chart is a 2.2. So 2.6 minus 2.2 gives us an electronegativity difference of 0.4. Electronegativity difference of 0.4, is that significant or not really significant? Not really significant. In fact, these delta minuses and delta pluses are so small that we typically ignore them. And so we don't call these bonds, yes, these bonds are slightly polarized because carbon has just a slightly stronger pull, but the cloud itself is going to look very symmetric. And so what we say is that all hydrocarbons, compounds of carbon and hydrogen, are nonpolar. It doesn't matter how complex the molecule is. The molecule can be very complicated. So let's take a look at some more complicated hydrocarbons. If we look at some complex, pretty soon they, this is kind of a little bit complex. This is what we call 2,2,4 trimethylhexane. Do you know what hex is? Six carbons. And so the way this is named is they pick the longest chain of carbon atoms, and they just try to follow it no matter which way it goes, because are Lewis structures accurate representations of the three-dimensional structure? No, they just show the linkages, so we just follow the longest chain. So we could have started here, we could have started here. We just look for the longest chain. The longest chain is going to be 6, so that's called the parent chain. And so the hexane, the ane comes from all single bonds, but we'll talk about that later. And then this is a 2,2,4 trimethyl. You know what meth is? Meth is, well, how many carbons is meth? Meth is one carbon. And so we have a 1 carbon group stuck here, 1 carbon group stuck here. So 2, 2. There's 2 1 carbon methyl groups. These CH3 groups are called methyls. And then if we look at carbon 4, what's attached to carbon 4? Another methyl. So this is why it's called trimethyl hexane. And the 2,2,4 just tells us the position of those methyls onto this chain. But when we look at it, are the carbon-hydrogen bonds polar or pretty much nonpolar? We classify them as nonpolar. They're very, very slightly polar. But if we have nonpolar bonds, it doesn't matter how complex the molecule is. The molecule is going to be nonpolar. And so what significance does that have? The significance that it has is that oils, hydrocarbons, and water is polar. They don't mix. Yeah. And so we have a rule, like dissolves like. And so polar likes polar, nonpolar likes polar, but they don't like the opposites. Sometimes there's so many carbons, it becomes a pain. It becomes a pain to draw out all the carbons. And so this is a shorthand representation. Sometimes they won't even show these end ones here. They just show it like this. And then what you're looking at is the carbon-carbon bonds. All the carbon-carbon bonds are shown. You can tell the hybridization of the carbon here. You know what it is? Oh, not hybridization, the geometry. The geometry is actually tetrahedral. So this is what the zigzag is. The zigzag are tetrahedral angles. And so when we look at it, we can look at it in different orientations, but when we look at it, it kind of zigzags here. And so we'll put 2 in the plane. If you put this one in the plane, and then we'll tweak this one so it's in the plane, and so we get this flat in the plane. This is tetrahedral. And so this is the zigzag part. Now, the hydrogens aren't shown. It's only but one hydrogen sticks out towards you, the other hydrogen sticks in. And so what we're looking at is this, zigzag. And then we have another tetrahedral carbon, flatten it, zigzag. This is what we did in the drawing on Thursday. We made a zigzag pattern. That zigzag pattern is this. And so how many carbons do we have? Here, 13 carbons in the longest chain. Tridecane is what it's based on. And then we have on carbon 3, we have a 2-carbon thing. On carbon 3, a 2-carbon is what? Called what? F. And so on carbon 3, we have an F. Do you see that? It's 3-ethyl. On carbon 7, we have 2 groups. These are more complex. So we aren't going to get into the name of that because it's beyond the scope. Just simple one we'll look at. But, no matter how complex it is, hydrocarbons are nonpolar. They're like oil. And so it could have the weirdest looking structure, but nonpolar. Oh, no, this is not a hydrocarbon. What makes this different than a hydrocarbon? Yeah, on the end. This is kind of like a carboxylic acid. There's a carbon here. This carbon here is trigonal planar here. There's a carbon here. And so this is a trigonal planar where we have a carbon-carbon bond, a carbon-hydrogen bond, and a carbon-oxygen bond. Okay. It kind of looks like a carboxylic acid, but one thing's missing, an O. And so this is called an aldehyde. Aldehydes are not like oil. Aldehydes are what we call polar. And, typically they're polar. It depends on how long the chain is. So let's take a look at some of these molecules here. So it doesn't matter what this is, like this. This is what we call nonpolar. But over here, carbon versus chlorine. Carbon versus chlorine, chlorine is much more electronegative. And so chlorine is going to suck the electron density away from carbon. So these bonds are polar here. These bonds are polar, but an interesting thing about tetrahedral is tetrahedral has something called spherical symmetry. If you look at this kind of looks like a ball. And it is like a ball because all the angles are the same. Everything is equal. Each tetrahedral site, if you grab it from any end, it looks exactly the same. And so this is what we call spherical symmetry. And so if you put this inside a ball, it'd be balanced. This would be balanced. And so what happens here is this. What we're looking at is, do the bond dipoles add up to a molecular dipole? And so these are the bond dipoles here. We've got a positive and negative end, positive and negative end. And so do the bond dipoles add up to give us a net molecular dipole? And so the way this is going to look is like this. How do I draw a tetrahedral? Tell me. Where should I put the lines? Where should I put the wedge in that? Well, you should be able to do this. Yeah. And then we'll throw out the chlorine. So is this molecule like oil or is it like water? Is it polar or non-polar? So those are what we want to figure out. And the way we figure it out is that we look at the bonds first. The bonds are polar. The bonds are going to be polar like this. The electron cloud is going to be pushed to or pulled to chlorine. And so this is the way we're going to show it. The electron cloud is going to be distorted towards chlorine. Chlorine is more electronegative. And that's going to leave this end positive, this end negative. And so the way we're visualizing it is something like this, where the electron cloud is polarized. resulting in a negative charge here and a positive charge here. So these are two representations, three representations showing the same thing. One showing the distorted electron cloud, two showing bond dipole using delta pluses and delta minuses, and three showing a bond dipole using an arrow with a positive tail. Normally we'll just show the arrow with positive tail, so it's going to be like this. And then what we do is something called vector addition. Vector addition, we're doing is we're going to try to add up the arrows in 3 dimensions. This is kind of hard to add up, but imagine a tug of war. If you had a tug of war, and let's say these are the chlorine atoms here. The chlorine atoms are pulling on the electron density, like this. If you had a tug of war, is this black ball going to move in one direction? Let's say these two are pulling down, right? These two are pulling down, so therefore this black ball should be pulled down, correct? But these two are pulling up, equal and opposite. And so this is spherical symmetry. So what happens is, in 3 dimensions, these bond dipoles cancel one another out. And so there's no net. So what we do is we sum up the bond dipoles. And so the sum of the bond dipoles is equal to 0. And therefore this is like oil. It's nonpolar. This is a very dense oil. This oil, this is called, do you know what the name of this compound is called? CCl4. Carbon tetrachloride. Carbon tetrachloride is dense. It sinks in water rather than floats like oil, but carbon tetrachloride and water don't mix. They don't mix. All right, here we can see what they're showing here is this. Now, carbon-hydrogen, is that much of a bond dipole? Carbon-hydrogen? No, we ignore that. And so essentially what we have is one pulling this way, one pulling this way, one pulling this way. So if this atom isn't pulling at all on this bond, then we just have these 3 pulling down. If these 3 are pulling down, the net movement is down. And so what we're going to do is we're just going to flip it on the side. If we flip it on the side, then the net movement is out. This. And so we have a net, what we call a net dipole. This is the molecular dipole. Likewise, if we did this, I actually have enough balls for this one. So this is it, except the greens are supposed to be the chlorine. I only had 2 greens that I could find back there. But here we have this molecule here. So carbon-hydrogen is nonpolar. Carbon-hydrogen nonpolar. Carbon-chlorine, polar. And so if I have a bond dipole pulling up like this and a bond dipole pulling up like this, do you see the net movement? The net movement is going to be out that way. And so the molecular dipole points straight out like this. Here. The net movement is this way. And so this molecule should be polar. This molecule should be polar. This molecule should be polar as well. So let's take a look at that last molecule there. So again, hydrocarbon, ignore those. It's just one. And in fact, the bond dipole and the molecular dipole are the same thing. It's just pulling straight up. Normally we draw like this. These 2 in the plane, one coming out, one going in. So this would be the wedge coming out. This would be the dash coming in. These 2 would be in the plane here. Sort of the way we're orienting these molecules. So that's polar. CO2, the shape plays an important role. CO2 has polar bonds. The carbon, oxygen, the oxygen is more electronegative, so the bond dipole is going to be towards oxygen. This is going to be the negative. We draw the arrow. We could draw this arrow here, this way. be on the carbon, the opposite arrow here. But if you have one arrow pulling this way and another arrow equal and opposite pulling 180, then you're going to cancel each other out. And so CO2 is nonpolar. CO2 and water don't mix. That's why bubbles of CO2 bubble out of water. They don't mix. Water and water mix. Does water mix with water? Yeah, water mixes with water, and it's perfectly fine. That's because water is very polar. And so when we have one bond dipole pulling up here, another bond dipole pulling up, the net movement is going to be straight out. That will be the net dipole here, the molecular dipole. So water is very polar. Organic compounds can either be polar or nonpolar, it just depends. All hydrocarbons are nonpolar, but there are lots of different types of organic compounds. And so we're going to look at some organic chemistry right now. Organic chemistry is the study, research, and application of carbon compounds. Not all carbon compounds are considered organic, like CO2. Is CO2 considered organic or inorganic? Inorganic. Carbonate, you know, like in calcium carbonate, is that organic or inorganic? Inorganic. Cyanide's considered organic. And so those are some historical distinctions. Most carbon compounds are considered organic. Carbon atom is the right size and strength to form chains. Does oxygen like to form chains? 2 atom chains at the most, but anything more than 2 atoms, forget it. Like a 3 atom. 3 atoms ozone, and this is very unstable. But carbon, no problem. 2 atom, 3 atom, 13 atom, no problem. It's no problem. And that's why carbon chemistry is so rich, you know, when you compare it to oxygen chemistry. Inorganic chemistry is the rest of the periodic table. And so it just goes, and when you look at the total number of compounds, let's look at the total number of compounds from all the elements in the periodic table except for carbon is in the less than 1 million, I think, the known ones, maybe around there. But the total number of compounds for organics is huge and growing because they're making new ones all the time. And so, or discovering new ones too. So organic chemistry is just that one element. Well, that one element plus other elements makes it for extremely rich chemistry. So this is why the periodic table is divided. However, carbonates, I guess cyanide. Cyanide's considered inorganic, sorry. Not considered organic. Oxides of carbon, like carbon monoxide, carbon dioxide, and a few other containing carbon compounds are often classified as inorganic. There's a typo here. That should be, yeah, there should be no space there. Inorganic's one word. So let's look at the hydrocarbons. Hydrocarbons are organic compounds that just consist of hydrogen and carbon. There are different types of hydrocarbons. There's the alkanes. Alkanes are like methane, ethane, propane, butane. Those are all alkanes. One thing that alkanes have is they have all single bonds. You know, the carbon-carbon bonds are all going to be single. There are going to be no double bonds, no triple bonds. If there's a double bond, we don't call them alkane. If there's a triple bond, we don't either. We call those alkenes and alkynes. So alkanes are going to have all single bonds. So let's look at some alkanes here. What's the longest chain of carbons here? 1, 2, 3, 4. 4 carbons would be butane. Do you see the zigzag pattern? It's zigzag because they're tetrahedral, and zigzag because we're going to flatten it out like this. So we can just draw it. Otherwise, we're going to run out of space. Or, of course, there's bond rotation, so I could flip it, you know, different conformations. So this is called normal butane. But this is the same exact formula. Same exact formula, but different structure. When we have the same exact formula, well, I shouldn't say same exact. These two formulas are different because these two formulas are called structural formulas. But if we look at the molecular formula is C4 C4H10 for N-butane. Isobutane is C4H10. Both of these are C4H10, but structurally they're different. And also their properties are going to be different. And so this one goes by two names. So this is N-butane, and this is isobutane. Iso has this little fishtail on it. Or alternatively, what's the longest chain you count here? 3. And so this would be called 2-methylpropane. 2-methylpropane and isobutane are the same thing. 2-methylpropane would be its systematic name.
So you read it from left to right?
No. You read it from right to left or left to right or top down or bottom up.
So how do you differentiate between, say there's one at 2 or there's 2 at 2 and there's like.
How do you differentiate? Good question. Let's take a look at this one here. How do you differentiate? What's the longest chain?
4.
1, 2, 3, 4. So this is butane. And so should you call this 2-methylbutane or should you call it 3-methylbutane? 2-methylbutane or 3-methylbutane?
2-methyl.
Well, actually they're the same thing. 2-methylbutane and 3-methylbutane are the exact same thing, but we got to choose one because we don't want two names for the same thing. And so the rule is this: you always go with the lowest number possible. And so the correct answer would be 2-methylbutane. And it doesn't matter. It depends on who draws the formula. It's not left to right. It's not right to left. Because somebody might draw it differently. It just depends on how that person draws it. And therefore, we number it any way, upside down, right side up. It doesn't matter. We're going to number it such that the methyl falls on the lowest number. This is called, these are isomers of pentane, isomers of C5H12. C5H12 could be N-pentane or 2-methylbutane or isopentane. Iso, remember, has this little, what we call the fishtail at the end. This is neopentane. Neopentane has this tetrahedral, spherical shape to it, like a ball. This is neopentane. Give me another name for neopentane. Yeah, that's good. Heard it. This would be 2, 2 hyphen. Then I heard dimethylpropane. Propane, because 3 carbon. 2,2-dimethylpropane. Each methyl has a carbon, so there's 2 from the dimethyl and then the propane is all together 5 carbons. Or neopentane. A long time ago we went over the, do you guys recall the prefixes? Meth, F, pro, but, pent, hex, hept, oct, non, dec. Yeah, those are all right, those are the alkanes. There's also things called alkenes and alkynes, which we're skipping. And we're going to alcohols and ethers. I think so. Were the alkenes and alkynes in your book? No, then we're skipping it. Alkenes will just have a double bond. Alkynes will have a triple bond in there.
So it's not going to be on the list.
That's not going to be on the list. But, ethane is carbon-carbon single bond. Ethene, carbon-carbon double bond. Ethine, carbon-carbon triple bond. But all of them have 2 carbons. So. Let's look at alcohols. Alcohols are going to have the hydroxyl group. It looks like a hydroxide ion, and so it looks like a strong base, but it's not. What differentiates this from becoming a strong base? Is methanol a strong base? So let's take a look at methanol right now. do kind of the zigzag here. If I do the zigzag here, then oxygen is going to have a lone pair that sticks out, right and bold like this, and a lone pair that sticks in, like this. So imagine this is the oxygen in the center here. This is the carbon here, the hydrogen here. Then the one lone pair sticks out, one lone pair sticks in. This is tetrahedral here. This is also tetrahedral, but its molecular geometry is not tetrahedral. What is the molecular geometry of the oxygen? The molecular geometry of this oxygen is trigonal-planar. We're looking just at the atoms. If we look at the atoms, it's bent. Yeah, it's bent.
Oh.
This is a bend. You know what the bond angle is? HCH angle here? What is it?
The angle?
Yeah, what is the angle here? HCH angle. 109.5. The HCO angle should be 109.5, all single bonds. However, this COH angle, what's the ideal angle for the COH?
120.
No.
Less than 1.
Well, what is the ideal? The ideal is
180.
no. What is the angle in this thing here? 109.5. The ideal is 109.5, but I have a lone pair here and a lone pair here.
So 4.
Those push these two in, distorting the angle slightly to about 105. Good. That's that. Well, this is this an hydroxide? You know, is this a powerful base? You know, hydroxides are a powerful base. Is this a hydroxide? Is methanol a good base? All hydroxides are good bases, aren't they? Oh, the soluble hydroxides are good bases. In other words, is this a hydroxide or is this an alcohol? This is an alcohol. Well, are alcohols strong bases? No, why not? It has no OH like sodium hydroxide. Sodium hydroxide has no OH. Sodium hydroxide is a strong base. Why is methanol not a strong base? Sodium hydroxide and methanol are totally different. Sodium hydroxide is the ionic bond, so so we're dealing with hydroxide really here, but the carbon-oxygen bond here, what would you classify this carbon-oxygen bond as? Ionic? Covalent? If it's covalent, is it nonpolar or polar covalent?
Not polar.
If this bond would be polar covalent, and so the difference is the bond. The ionic bond versus a covalent bond. When water molecules come, they can tear apart the ions. So we'll get hydroxide ions and sodium ions. When water molecules come here, are they going to tear apart the methanol molecule? No, they aren't. Methanol stays together. We call methanol a non-electrolyte because it doesn't break apart into ions. Non-electrolytes don't break apart. Whereas sodium hydroxide is what's called a strong electrolyte, which breaks apart into the ions when you dissolve it in water. And so it kind of sounds like hydroxide, but it's not hydroxide, it's hydroxyl. You know, we have methyl, hydroxyl. These are, you know, these are kind of like radicals. The origin of the name comes from the free radicals. This is called the methyl radical. Is the methyl radical happy? No. What do you think the methyl radical wants to do? It wants to bond. This is called a dangling bond here. It's unhappy. methyl's unhappy. The same thing with hydroxyl. This is the hydroxyl radical. Is it happy? No. It's going to want one more bond. But, you know, we call it the hydroxyl group because in an alcohol it's found a bond right here. And so if we break this off, we break it off in the middle here with one electron to that and call it the hydroxyl. So we'd be left with a methyl and a hydroxyl. Methanol is also called methyl alcohol. You know, this is methyl attached to the alcohol hydroxyl group. An ether is going to be a little bit different. You know, an ether is going to have a different link. Alcohols have the COH link. Alcohol. Ethers are going to have a COC link. COC link. So let's play around with some ethers. You tell me the name of these ethers. What do you think the name of this ether is? What do you call this group, the CH3 group here? Methyl.
Is it dimethyl ether?
Yeah, that's right. This is called dimethyl ether. Dimethyl ether. How about this one? Not tri. It's going to have a methyl on one end and a ethyl on the other end. So this would be, it depends on which one you would do first. Will you do the methyl first or the ethyl first?
Methyl.
Maybe the methyl first, maybe the ethyl first, you know, it depends on the rule. Maybe it's alphabetical. If it's alphabetical, then you would do the ethyl, the ethyl methyl ether. Or it might be the opposite. It could be methyl ethyl ether. And so methyl ethyl ether or ethyl methyl ether. Let's take a look. Methyl ethyl ether. Oh, wait a minute. Here we have ethyl methyl ether. Here's ethyl methyl ether. We have ethyl ether. Do you know what ethyl ether is? Ethyl ether has ethyls on both sides. Diethyl ether. So what do you think it is? Is it ethyl methyl or methyl ethyl? Looks like it's ethyl methyl, which means alphabetical. Alphabetical. Which one? This one? Oh, well, this is a different one. This is methyl terbutyl. So methyl M versus T. This is methyl on one side of the ether. On the other side, we call this a T-butyl group. T-butyl group would be 4 carbons in this tetrahedral type arrangement. It's the T-butyl substituent. So looks like this. You just learned some substituents are pretty easy to name. You know, if you learn a few of the substituent names, let's take a look at organic substituent names. Substituent names like T-butyl. You know, if you learn some of these, you can name a lot of different compounds. So we learned the methyl, CH3, ethyl is CH2, CH3, propyl, CH2, CH2, CH3. This is isopropyl. Iso has this little fish tail. So isopropyl alcohol would have this fish tail thing, and what would you think would be attached here in isopropyl alcohol? Well, alcohols need a OH, so there's going to be an OH here. That would be isopropyl alcohol. Isopropyl alcohol is also called isopropanol, and it's also called 2-propanol, because on carbon number 2 you'd have the alcohol group. Then we have isobutyl. This is called secondary butyl. It's attached to the second carbon of a butane chain. Do you see that? So it's sec-butyl. This is called T-butyl. T-butyl because it has this tetrahedral type thing that's attached to it. That's T-butyl. There are others here. It goes on. You know, we have methylene groups, methylene bridge. But those are not really substituents, those are structures. Let's see if I can find it. Ones with the halides. Okay, take too much time. We have chloros. What do you think chloro is? Chloro would just be a chlorine atom on there. We have fluoros, chloros, bromos, iodos, those types of things, substituents. You can go down. Oh, here, this is more of the table of substance form. Oxocarboxy, depends on, you know, as the structures get more and more complex, then we have to use more and more of these names. This is called amino or amine, fluoro, chloro, bromo, etc. So this would be methanol or methyl alcohol. This would be butyl alcohol or butanol. You can see the zigzag chain of tetrahedral carbons, tetrahedral, 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 followed by the alcohol group. This would be bent here. Ideal angle is 109.5 because this has a tetrahedral electron pair geometry or EGG electron group geometry or set geometry. But the molecular geometry itself is bent. So it's zigzag. It's kind of zigzag. When we draw these, you know, we always draw it the same. 2 bonds in the plane, 1 bond sticking out, 1 bond going in. 2 bonds in the plane, 1 sticking out, 1 going in. 2 in the plane, 1 coming out, 1 going in. So we would do it. This one would have 2 in the plane, here, 1 sticking out. You can't see his lone pair, and 1 sticking in, which is a lone pair. We got the hydroxyl group. Now, an interesting thing happens. You know, methanol is very polar. Methanol is very water-like. You know, if you mix water with water, is there any limit to how much water you can mix with water? No. So water is what we call miscible in water. You can mix in all proportions. Methanol is the same thing. Is there any limit to how much methanol you can mix with water? No. Methanol and water are so similar that they mix like water and water. However, is there a limit to how much butanol you can mix in water?
Yes.
Yes, there is. Can you mix very much butanol? No, you can't. Why? Why is butanol so unfriendly with water, whereas methanol is so friendly? Yeah. It's because of this guy here. What does this look like to you? We call this the alkane portion. The alkanes are what? Alkanes are hydrocarbons, right? Single bonded. This is oil, and this is water. And so the oil part of this is not so big, not a big deal. This would fit in there. But as that oil-type portion grows, this nonpolar hydrocarbon chain grows, it becomes more and more oil-like, less and less water-like. And so there's a transition. Methanol is what we call miscible in water. It's like mixing water and water. Ethanol is miscible in water. Mix any proportion. Propanol is highly soluble, but when we get to butanol, what do you think about pentanol? Is pentanol going to be better or worse?
Worse.
Worse. Yeah. Pentanol, hexanol, those are insoluble in water. Ethers are pretty soluble, like dimethyl ether. What is this one called? Do you recognize this? This would be diethyl ether. Look like this. Here we set up the zigzag, but they tilted it a little bit. Do you see how they tilted it? Can you visualize that? Yeah. I didn't want them to tilt it. I wanted them to draw it as is, but usually you put two in the plane, so we twist it, put two in the plane, like this. The end here. And then this one would zigzag out like this, so it would be like this. It should be like this, where this one doesn't go down, it should go up. This one should go up, But they tilted it. It's not normally drawn like that. This one is okay, but this last methyl group here, they probably should have rotated it, put two in the plane. But it's kind of rotated, it's kind of there, off just a little bit. This is a methyl, but what is that? 6 carbons is called hex, but this is a very special 6-carbon ring. A typical 6-carbon ring would be a hexane, but since it's a ring, we call it cyclo indicating ring. So cyclohexane would be a ring of 6 carbons. But this one is special because it has double bonds here, and those double bonds are alternating. When we have alternating double bonds like that, we call them aromatic versus aliphatic. And so it has special properties associated with that alternating double bond number. This is called a benzene ring, or phenyl. Phenyl or benzene ring. And so as a substituent, we call it phenyl, C6H5. So that would be methylphenyl ether. Methylphenyl ether. Okay, those are some alcohols and ethers. Now we're going to go to carboxylic acids. All carboxylic acids are going to contain the carboxyl group. The carboxyl group is this. COOH. Your names are going to end in weak acids. These are all weak acids. All carboxylic acids are weak, except there's one that's pretty strong for weak acid. That would be like trifluoroacetic acid or trichloroacetic acid. It's fairly strong. So let's take a look at these weak acids. The first one is called methanoic acid. Methanoic acid, 1 carbon. But nobody ever calls it methanoic acid. Do you know what everybody calls this acid?
Formic acid.
Formic acid. Nancy's formic acid, which self-defense. You know what this one should be called?
Acetic acid.
Well, it's called acetic acid, but what is its proper name? This should be called ethanoic acid, but nobody calls it ethanoic acid. Pretty soon nobody calls it ethanoic acid. People forget what ethanoic acid is. It's like this, dihydrogen monoxide. Does anybody call it dihydrogen monoxide? No. Everybody calls it water. And so nobody calls it ethanoic acid. Nobody calls it methanoic acid, but people do call this propanoic acid. So let's take a look at the structure here. What is the geometry on this one? No. Trigonal planar. This one is bent here. How about this one on the left? Tetrahedral. Trigonal planar. So the angles here are going to be 109.5, and then this angle, trigonal planar, should be at 120, good. And this angle should be at 109. 109. It should be, but it's going to be distorted a little bit. This one? Trigonal planar and bent. We can see, we can see the EPGs as the set geometries based on the Lewis structure here. So this one's going to actually be tetrahedral, but it's going to have a molecular geometry that's bent. This is trigonal planar, both in electron geometry and molecular geometry. And these two are both tetrahedral in both electron or set geometry and molecular geometry. All these are polar. So these should dissolve in water. However, acetic acid is very soluble in water. What do you think about butanoic acid? Less soluble or more soluble, or about the same solubility? Butanoic acid than acetic acid. Which one should be more soluble in water? Acetic acid. How about hexanoic acid? Is hexanoic acid very soluble in water? No. Not very soluble. These acids stink. They have an unpleasant odor. Butanoic acid. Do you know where you can find butanoic acid? It's also, how about butyric acid? Maybe butyric acid. Butanoic acid. No, it's something else. Well, butyric acid, also called butanoic acid, is an acid that forms when butter goes rancid. Continue. Slideshow. Okay, that's chapter 13. That was the end, the little section on organic chemistry right at the end of chapter 13. Chapter 13 is kind of an important chapter, so maybe what we'll do is we'll take a look at some. This chapter 14, we're going to revisit gases again. Let's do a quick review. Chapter 14. Chapter 14, we're going to look at another law called the ideal gas law. The ideal gas law is incredibly useful. We're going to be doing ideal gas law calculations.
What is the next exam? What does it cover?
I'll probably cover chapter 14 too.
So chapter 14?
Wherever we left off last time. And then,
It was 10.
so 14 is got some stoichiometry and some ideal gas law equations. So two main topics in chapter 14, but it's not that bad conceptually. And it's not super long, so we'll take a look at it. Since gases were divided up into two chapters, we'll look at that one again. Let me go back to Cengage. Let's take a look at some of the homework. Did I assign chapter 13 homework?
No.
Oh, shoot. Forgot to do that. I need to do that. I'm going to assign chapter 13 homework. coming up to but we can take a look at some sample problems here for a few minutes and we'll go on break here. From chapter 13. So you get an idea. Since I didn't assign it yet, we can get just a glance at the homework here. See what we're dealing with. Drawing Lewis diagrams for these. Some small molecules and some ions here. Hydrogen. What do we call this one? Hydrogen iodide. Hydrogen iodide is very polar. It's soluble in water. When you dissolve in water, it forms hydroiodic acid. Hydroiodic acid we know is a what? Strong acid near the top. Hydroiodic acid, strong acid. What about it, metathesis? How about iodide? Is iodide a strong base? No, iodide is an extremely weak base. How about the metathesis properties? Yeah, H plus will react with any base stronger than iodide. How about the metathesis properties of iodide? Iodide. What is it? Chlorides, bromides, and iodides.
Mercury,
Close. Very close. Silver is right. Mercury 1 is right. And no. Lead 2. Okay. So iodides, this is precipitated. So if we react this with silver ions, mercury 1 ions, or lead 2 ions, we're going to get a precipitate of iodide. Silver iodide, mercury 1 iodide, or lead 2 iodide. Redox properties, H plus is an oxidizer. Iodide is what? Iodide is a reducer, and it's a decent reducer, although H plus is not strong enough, so it's stable. H plus is not strong enough to oxidize iodide, but there are plenty of other things that are strong enough to oxidize iodide. It's not so difficult because iodide is a big atom. So it's got some redox. So this is pretty interesting, HI. This has got some acid base, it's got some metathesis, and it's got some redox properties. Water isn't this interesting though, chemically, which is maybe it's a good thing, because water, is a strong acid? No. It's a strong base? No. Does it participate in metathesis reactions? No. Redox? Yes, but it's very weak both ways. Right? And so we analyze these things as we go down. We try to get more familiar. What's this called? Trichloro. No, normally we call it, according to our rules that we learned in nomenclature, we call it nitrogen trichloride. There's another name for it. It's trichloramine, or nitrogen trichloride. But the mean would be a little bit of a different type of scenario, because if you think of an amine. Well, let's draw the Lewis structure for this. If we draw the Lewis structure, actually we're going to go beyond drawing the Lewis structure. You know, because if you draw the Lewis structure, what does it look like? But this doesn't really show the shape, you know, what would the CL angle be?
John?
109.5, it's gonna be distorted. So how should we draw this? Typical way we draw this, we put a lone pair in the plane, and then a bond, one of the bonds in the plane. That means one bond is gonna come out. One bond goes in. What do we call this shape? This shape called? It's tetrahedral set geometry, but the molecular geometry is not tetrahedral. What is it?
Pyramidal.
Trigonopyramidal. Yeah. This is a trigonopyramidal molecule. It's kind of like ammonia. You know, if we're thinking about the properties of this, we might think about the acid base. If we're thinking about the acid base, maybe it's similar to ammonia. Ammonia is being a weak base. But when we look at this, this is a bit different. It's a bit different. And so I told you that we use our electron counting system to understand the properties. And so when we look at the formal charges here, are there any formal charges? No. Just like ammonia, there's no formal charges. But sometimes what we'll do is we'll look at the oxidation state. And so is ammonia and this nitrogen trichloride similar in base properties? You might think, yeah, they look kind of similar because you got nitrogen there, they're both trigonopyramidal, right? But the electron counting tells us how the electron density of the electron cloud is distributed. And so the formal charges are 0 and 0, but when we look at the oxidation states are not the same. What's the oxidation state here on nitrogen? Yeah. -3. What's the oxidation state of the nitrogen here?
0. No.
+3 is correct. Yeah, +3 is the oxidation state here. Do you see those two nitrogens are kind of opposite of each other? So this one acts as a base, this one's not going to act as a base. So this will be a weak base. You know. Things that are like this will be a weak base. These are called amines. This isn't really an amine here. Amines are weak bases, like ammonia. This is different. In fact, the same can be said about the redox too. When we look at the redox, you know, this one is electron rich, electron poor, or electron rich. How about this one? Electron poor. So they're opposite ends of the redox as well. And so this is what we do in trying to analyze some of these. We look at the three-dimensional structure as well, because the three-dimensional structure will tell us some additional information. And so we got to draw out the Lewis structures to some of these. And then we have some isomers going on here. This is going to take a minute to go over there. All right, then we'll go on break here. Take a look at some more problems.